I'll talk about the deeper stuff, and it will help you all to understand these models better if you know just one or two things about seismic waves. So this is an earthquake that happened in Narangara back in 2023, recorded in one of our devices. There are three component devices to record the 3D ground motion, so Z, north and east. And we see so P, compressional waves, shearing waves, and lagging that, surface waves, and they turn up to differing degrees on the different components. So P and S, these being body waves, named because they travel through the body of the Earth, and surface waves that rumble along through the surface or close to the surface. This is a local earthquake here in WA, but to see deeper, we need a bigger bang. So we go to teleseismic earthquakes, so those that occur, say, of plate boundaries surrounding Australia and further afield. This is a silly example to motivate a serious point. So these are two stations from phase 1. So in the vicinity of Coolya Nobbing of iron ore fame. And we see something that doesn't look like an earthquake. So it doesn't have a P, doesn't have an S, doesn't have a surface wave. Instead, it's a rumbling that rises to a crescendo and dies away. So it's a train. It's close to the train line. All right, and then 40 kilometers to the east of that, we have the train rumbling past again, and you can work out speed. So it's 80-something kilometers per hour. It all makes sense. But eagle-eyed among you, you'll notice these other signals that are apparently buried in that. So around 1400 seconds, we see something, around 1000 seconds, we see something coherent on both seismograms. So I apply a filter to WBQ18, and so we see an earthquake. So this was from the I think it was the Solomon Islands, a magnitude 5.8, a couple of thousand kilometers away. And again, we see P waves, S waves, and the surface wave. But in this case, those waves have a chance to interact with the internal structure of the Earth. So we get reflections, bouncing off stuff. So we get a family of P, a family of S, and the surface waves. Now, the thing you should take from this is the steep inclination angles of the body waves at these teleseismic distances. So they're all shooting up almost subvertically, and the surface waves will trundle along close to the surface. This is another example. So this was the large earthquake that happened in Morocco a couple of years back, and it's the same thing. So we get a family of P waves, a family of S waves interacting with the core to various degrees, followed by the surface waves. In this case, the quickest path was through the core. All right, so one last example. This was from an earthquake that happened in the vicinity of Vanuatu on this most recent phase. So again, we see the P, the S, the Rayleigh waves. So I'm going to focus on the Rayleigh wave here. So this is a surface wave. It's got this characteristic shape, so it's drawn out toward the front, like an accordion. So that lower frequency energy, it travels faster. It does so because it's sensitive to deeper depths within the Earth, where everything's a bit more rigid. So, and by looking at in different frequency bands, in effect, we're looking at different depth intervals within the Earth. So period is a proxy for depth. And this is the value of surface waves. So they have very good vertical resolution, so we can back out things like LAB depths. But their lateral wavelength is quite long, so they're going to be smooth models laterally, but good depth resolution. All right, and so we do this, we capture surface waves from hundreds of earthquakes recorded across, so WA Array, Swan before that, Alfrex before that, and the national stadiums, and we put them into the tomography machine. I'm just going to present the models here. I'll talk more about what they may mean later this afternoon. So what you have to understand, so blues are seismically faster, reds seismically slower. The value of surface waves is that they give you an absolute wave speed. So these waves are transiting laterally at the surface. I have a station here, I have a station here. I measure an absolute wave speed. It might take 10 seconds to travel between them. That tells me about it tells me something about the geology. So these are slices at 75, 100, 125, 150, and so on. So things to note here. So the wave speed, so the shear wave of global average continental structure, that's indicated by AK135 on each color bar at each depth interval. And then I've done something similar, the average global speed for cratons. So it's really at the transition between greens and blues. So you can see that large portions of the West Yilgarn are above that, and it's known to be globally seismically fast for a craton. All right, and so looking at the same thing in cross sections, so the locations of the cross sections shown superimposed on the first slice at 75 kilometers, so A in the north through F in the south. So again, we see this seismically fast, thick type unit in the west, transitioning to thinner stuff in the east. So I've also got a seismological LAB proxy that I've backed out of this. In reality, it's a transition, but we'll call it a boundary for our purposes. The derivative map is shown on the top left. So LAB depth with the thicker colors are in blue, the shallower colors transitioning to the browns. The relative variations are better determined than are the absolute values. So you can apply a DC shift to these up or down. So again, it's the lateral variations that we should trust. And with that in mind, I've also calculated a lateral gradient map on the bottom left. As I said, I'll talk more about what this might mean this afternoon. So shear wave splitting. So this is another view into the lithospheric mantle or the upper mantle. So seismic anisotropy, this is a directional dependence of seismic wave speed. And if we're talking about the upper mantle, it's thought to be rooted in this. So this concerted alignment of olivine under stress. Now that could be fossil fabric frozen into the lithospheric mantle at the time of, or the last tectonothermal event, or you could have a big signal from active strain in the asthenosphere. And I think a nice example to provide context. So this is from southeastern Australia. This is led by collaborator Caroline Eakin from ANU. So what do we see? So absolute plate motion for Australia is roughly to the north. So we have thinner lithosphere in the east, and then moving to the west into the Gawler. We're transitioning to thicker lithosphere. So we see this signal where it's probably more due to asthenosphere in the east, and then something fossil in the lithospheric mantle in the Gawler. So this is from shear wave splitting. So Miriam, who is Caroline's postdoc at ANU, is leading this work. So I should have said that the bars represent the strength and the orientation of the fabric. So the longer the bar, the stronger is the anisotropy and the splitting of the shear wave, and the bar gives its orientation. So the interesting thing about the Yilgarn, you get these predominantly east-west fabrics, and they align with these 2.4 GA dike suites. Now, Miriam's interpretation is not that this is caused by the dikes, but rather the dikes are in that orientation because of an older east-west fabric. But it's interesting that the east-west fabrics are so pervasive across the study area. All right, and then we can superimpose those fast polarization directions, those indicated by the white bars, on the surface wave tomography model. So I'm showing this at kind of two characteristic slices, one at 75 and one at 150 kilometers depth. So that was the surface waves. That was shear wave splitting, waves that travel through the core, and now P wave tomography. So this is led by colleagues in China. So again, we've got these. We're relying on teleseismic body waves. They're steeply inclined, so you can imagine a plane wave coming up instant on our array. I no longer have that absolute wave speed of a laterally transiting surface wave. I could step from here 40 kilometers that way. If the wave is coming up, it might be arrive a couple of fractions of a second earlier there than it does here. So we can only then infer relative velocity variations. We lose that absolute background context. But these are higher frequency waves, so we get much more lateral granular detail. But that vertical preponderance of the ray paths means that it's very hard to localize at which depth it's accruing these time differences. So better lateral resolution, worse vertical resolution. What did the data look like for this relative arrival time tomography? So these are the delays. So clustering the earthquakes by quadrants, so earthquakes from the northwest. So arriving relatively earlier, I suppose, maybe within the Yellowgarden, and a bit slower at its edges, to varying degrees according to whichever quadrant they come from. So that's the raw data. Then you put that into the body wave tomography algorithm, and we produce something like this. So it's a much busier model as anticipated than the surface wave model. So we're getting that granular detail, but without the same depth constraint. Then I can compare the models. So surface wave models, 75 and 150 kilometers, body wave models at various slices from 75 to 250. The body waves we'll see deeper. With an array of this aperture, you can see, you're pretty much seeing to the transition zone. The surface wave stuff, we might get to 250 kilometers-ish. And then, so sticking in the derivative LAB model in the middle, the lateral LAB gradient model, bottom center. And I'm gonna stop there, and I'll talk about this stuff, what it might mean later this afternoon.